like to welcome you to that little presentation about ancient mathematics and modern aircraft construction. For that we have to do a little bit of theory, and then we will go into my aircraft shop and do the practical work. The ancient theory I'm talking about, and I will use later, is the Pythagorean theorem that says in a right-angled triangle, the areas of the square of the legs of that right-angled triangle equals the area of the base of that triangle. That's in a written form. There's also a form that is more clear. It's the geometrical form, and Pythagoras was the first one who proved that theorem. This theorem is known about 4,000 years or longer, and it talks about the area here and the area here. The sum of that equals the area here. We have the right angle in that corner. We will use that fact in a different way later, where we turn that a little bit. You have the right angle here and the base of the triangle on top. And the way this theorem is used, usually in our application today, is not so much the areas. We are talking about length of sides. How it comes out in the end is, if you know the length of two sides of a right-angled triangle, you can calculate, based on the theorem of Pythagoras, the length of the third side, which you might or might not know about. So let's go to my aircraft shop and see how this applies in real life. For our practical exercise, based on the theory we did in the classroom earlier. It's a Challenger XL65 aircraft. It's a light sport aircraft. You can fly it with a sports pilot license. It has its engine at the end. You see the engine in the prop. It's called a pusher because it's in the end. The engine is a 65 horsepower two-stroke water-cooled engine. The radiator for the engine is sitting on top of the aircraft with an angle. And here came my dilemma. This plane came as a kit, and I had to do most of the work myself. And the front assembly for the radiator had to be installed at a certain point. And the factory gave two measurements on two different pages. They gave 23 inches from the end of that the square root tube, and it gave 24¼ inch from the end of the radiator mounting. So we have two reference points, two measurements, but anyway, since we only have one part to install, we should have one point where it ends up, and it doesn't. As you can see, the two measurements don't lead to the same result. So I decided, instead of calling the factory and ask the person who made the mistake in the first place, to think about it and calculate the correct distance from the end myself. And as you can see, it doesn't match either one that they gave me. The result is 24¾ inch from the end of the rear assembly. And how did I come up with that solution? We go to the other side of the plane, because here we can see more clearly how this radiator is set up, because the engine is not in our way here. We have this shape, and as you can see, this is the right angle here. And we have three straight lines. That means we have a triangle with a right angle. That means we have a right angled triangle. And all we need to do now is to think about high school mathematics and use the theorem I mentioned earlier. So we have to measure two sides. One is the distance between the mounting holes on the radiator. It's 25¼ of an inch. The length of the front assembly is 5¼ of an inch. And since the rear assembly is not sitting directly on the root tube, it's a little bit level, we have to measure that too, and in the end we have to subtract it from that distance here. And this one is 5/8 of an inch. So we have a right angle, we have measured two sides, and now we are able to calculate the missing side, which in the end will lead to the 24¾ of an inch. So we can go back to the whiteboard and finish our calculation there. We are back to our screen here, and now we do the actual calculation based on the measurement we made outside. Remember, we have the theorem that talks about the areas, and applying this to the aircraft, you have the B, C and A, and applying this to the aircraft means, now this computer doesn't work with me, the right angle here, A, B and C, given was, as we could measure actually, A and C. So the length in question was the length of the side B, where I got two measurement points from the factory and didn't believe that one of them is true because they were different. So applying this and talking about area and length, we now see that this theorem is used for calculating length instead of areas, and that is done that way. We have to transform the equation. I make it quick because most of you might not want to go as deep into it as it is needed. We subtract A square from both sides to isolate B square. Then we pull the square root and have B isolated. So this is the equation we need. We have the measurement for C and A done in my shop earlier. We put that in the equation. We measured 25¼ for the distance between the holes on the radiator. We measured the length of that front assembly and had to subtract 5/8 of an inch, which makes it 4.6.25, and the whole equation leads to B equals the square of this minus the square of this, and taking the square root goes to 24.82, which is pretty close to 24¾ of an inch. And that is the measurement point which we came up with, and you saw at the aircraft earlier, and that's the point where I drilled the holes, and that's the point where you can also see, if you look closely, that the bolts of the front assembly go straight in the middle of the rubber grommets of the radiator. That means that the least tension that is possible for that assembly, and even if I taken the other measurements, one of these, it might have worked somehow, but it would be under tension, and I don't want to have this part of the radiator broken and flying to the prop during the flight. That was my little presentation about aircraft and ancient mathematics. I thank you for listening to me, and I hope that everybody has always happy landings.